We will be discussing the atomic mass and Avogadro's number. When we discuss the atomic mass, we're looking at the bottom number here. Notice it's not a whole number. That's because it's considering all the isotopes within that element. Not only that, but they're actually looking at how much it actually occurs in nature. So it's a weighted average, not just adding them up and then dividing by however many numbers you have. For instance, neon 20 occurs over 90% of the time, whereas neon 22 still occurs 9% of the time. So we have to take into account, but we want to make sure that the 90% one is actually more evident. And we can do this by taking the isotope weight and multiplying it by however much is observed in nature. For instance, gallium-69 with a mass of 68.9256 and abundance of 60%. Well, I got to take that 60% into account, so I'm going to change that to a decimal. I'm going to say 68.9256 occurs 60% of the time. So that relative average, the weighted average, is 41.43. Gallium-71, however, has a mass of 70.9247, and it occurs 39% of the time. So I'm going to change that to a decimal. And that's weighted average is 28.29. When I add that together, it's 69.72 AMU. Notice I did not just add the two numbers and divide by 2. That's the wrong way, because that doesn't take into account how often it's found in nature. So these numbers here have taken the individual isotopes and multiplied it by however much is found in nature, that percentage, and added them all together. That's why they're not whole numbers. So let's talk about the unit moles. The unit mole is used by chemists to count atoms. There are 6.02 times 10 to the 23rd particles in 1 mole, which gives us a conversion factor here. This is called Avogadro's number. Notice that the term particles is very broad. That's because it can account for atoms, ions, molecules, and formula units. There's 4 different things it could be. So you have to figure out what the representative particle is. Before you can figure out how to use the Avogadro's number. The value of a mole is the number of atoms in exactly 12 grams of pure carbon-12. And it is the base unit that can convert amongst other units within chemistry. So let's take a second to practice this. Determine the number of moles in 1.29 times 10 to the 24th hydrogen atoms. Well, when we're talking about Avogadro's number, there's 4 key terms to look for. We want to look for atoms, ions, molecules, or formula units. Those are the 4 terms you're going to be looking for in order to know to use Avogadro's number. Here we have the word atoms. That means I'm going to use the Avogadro's number. 6.022 times 10 to the 23rd atoms is equal to 1 mole. So the very first thing is to determine the conversion factor, and we did this. Then you put the given number over 1. I know I don't need any other conversion factors because I have the word atoms and moles where we're going from and where we're going to in the same conversion factor. So I'm going to put the number over 1 now. 1.29 times 10 to the 24th atoms over 1. Whatever unit is on top needs to be on the bottom of the next line. So I have atoms on top. I need to put atoms on the bottom of this line. Now I look at the conversion factor, and I look for the word atoms. I know I need 6.02 times 10 to the 23rd next to the word atoms. The equivalent to the unit from the conversion factor goes on top. So 1 mole then goes on top. Where you're coming from goes on bottom. Where you're going to goes on top. To put this in the calculator, there's a button you need to find. It either says EE or EXP. Sometimes it might be a second function. You're going to want to type in 1.29 EE 24 divided by, because it's on the bottom, if it's on the top you multiply, if it's on the bottom you divide, 6.022 EE 23. That's going to come out to be 2.14. The atoms cancel out, and you're left over with moles. Some of the newer calculators have actually started saying times 10 to the x. This is your last resort. Try to find these two first, because there's another button that looks very similar to this one. If you use the 10 to the x button, that's going to come out wrong. It has to be times 10 to the x. Most chances are you're going to have one of these two buttons on there. Alright, let's take another problem. This one's going to be a little bit harder. Determine the number of hydrogen atoms. I see the word atom there, so that automatically makes me think I need Avogadro's number somewhere. And 3.14 moles of H2O. We have a little issue here because it's asking for hydrogen atoms, but it's giving us water, which is a molecule. So the representative particle here for Avogadro's number will actually be molecules, not atoms. Because there are 2 atoms in every molecule. Okay, so do we have all the conversion factors? We're starting off with moles, and it's asking about atoms. So we're going from moles to molecules, then molecules to atoms. So we're okay. So we've done the conversion factor part. Now we need to put the given number over 1. 3.14 moles of H2O over 1. We have moles on top, which means I want to put moles on the bottom of the next one. Here it is in the equation. That equals 6.02 times 10 to the 23rd. I'm sorry, that the number 1 goes with moles. And that equals 6.02 times 10 to the 23rd molecules. I'm going to cross that out so it doesn't confuse me and I don't use it again. We have molecules on top. I'm going to put molecules on the bottom of the next one. I look for molecules, and I have the number 1. That equals 2 atoms. So for every molecule, there's 2 atoms of hydrogen. So it's going to be 3.14. It's on top, so we're going to multiply 6.022 EE 23 divide by 1 times 2. That's going to come out to be 3.78 times 10 to the 24 atoms. Determine the number of molecules in 4.9 moles. This one's a little easier. Notice Al2O3 is a molecule or a formula unit. So that means all I have to do is use the Avogadro's number, because that's what it's asking for. So 6.022 times 10 to the 23rd equals 1 mole. 4.90 moles over 1. 1 mole, because moles are on top, I need to put it on the bottom of the next one, is 6.02 times 10 to the 23rd molecules. And that comes out to be 2.95 times 10 to the 24. So the molar mass, that number on the bottom, is the mass of 6.022 times 10 to the 23rd particles. So for example, if we're looking at copper, that's 63.546. On average, if we counted up all the copper atoms, it would equal 63.55 grams. And then we can turn around and use this one in a conversion factor. So determine the conversion factor. You notice the word grams here. When we're looking at molar masses, we're looking for grams or mass. If we see one of those key terms, we're going to look on the periodic table for the molar mass. So I know that it's 63.546. And that's grams in 1 mole. Because that's by definition how many atoms. 6.022 times 10 to the 23rd atoms is 1 mole. So 0.88 moles. We have moles on the top. Let's put moles on the bottom then. Notice we're doing the exact same steps. Put it over 1. The units on top needs to be on bottom. The number 1 goes with moles. Its equivalent goes on top, so that's 63.546. If it's on the top, you multiply. If it's on the bottom, you divide. So 0.88 times 63.546, which comes out to be 55.92. There's 2 sig figs in the question, so that means we're going to round it off to 56 grams. Let's try that again. Now we're looking at aluminum. How many moles are in 43.7 grams? That means I need to look at the periodic table, because I see the word grams. I see the abbreviation for grams. So I look on the periodic table and I find that the molar mass of aluminum is 26.98. So we have the conversion factor because we can go from grams to moles in 1 step. Put the given over 1, so 43.7. Grams are on top, so I want to put grams on the bottom of the next one. 26.98. That equals 1 mole. The equivalent goes on top. Coming from, going to. So 43.7 divided by 26.98 comes out to be 1.6197. 3 sig figs, it comes out to be 1.62 moles. And the very final practice problem we're going to do with these is we're going to combine atoms with grams. So, how many grams? That tells me I need to look at the periodic table. So I look at the periodic table and I find that sodium is 22.99 grams in 1 mole. Alright, so we're looking for grams, so we have it here, but that gives us moles, but we're starting with atoms. You notice we see the word atom there. Atoms, ions, molecules, formula, units. We're going to use 6.022 times 10 to the 23rd. And A is an atom, so I don't have to worry about converting it from molecules to atoms or anything like that. Okay, so now we can go from atoms to moles, then moles to grams. We have our conversion factors. Now we're going to put our starting number over 1. We have atoms on top, put atoms on the bottom of the next one. 6.02 goes with those atoms. That equals 1 mole. We have moles on top now, so we need to put moles on the bottom, and the number 1 goes with moles. That equals 22.99 grams. So 5.34 EE30 divided by 6.022 EE23 times 22.99, that comes out to be 2.04 times 10 to the 8th. That's supposed to be an 8. Grams of Na. And that gives you explanation on Avogadro's number and atomic masses and how to use both.